So next we have Cayley-Hamilton theorem. Cayley-Hamilton theorem. It says that every square matrix satisfies its own characteristic equation. Every square matrix satisfies its own characteristic equation. What does it mean? What is the characteristic equation of a square matrix of order n cross n? Determinant A minus lambda n equal to 0. This theorem says that this is a polynomial in lambda. That polynomial, if you replace lambda by A, you will get a null matrix. Let us verify it for a or prove it for a 2 cross 2 matrix. Consider a 2 cross 2 matrix, general 2 cross 2 matrix. Say A equal to A, B, C, D. So first find the characteristic equation for it. Means determinant A minus lambda I2 equal to 0. This is the characteristic equation for this matrix. Now, if you simplify it, already you have done it earlier, what do you get? Lambda square minus see what do you get? Trace of A, that is A plus D lambda plus determinant of A, AD minus BC equal to 0. You can check it. This is the characteristic equation of this matrix. Now, according to Cayley-Hamilton theorem, if I put lambda equal to A, what I get? A square minus A plus D times lambda means A, put it A again here, plus AD minus BC times I2 you have to write because these are matrices now, A square and A. In matrices, you can add a matrix only. So don't leave AD minus BC as it is. It is a constant. You have to write unit matrix with it. Now, if you simplify it, means you write ABCD whole square means multiply this with itself. Minus A plus D, ABCD plus AD minus BC. I2 means unit matrix of order 2 cross 2. If you simplify this, square it and add and all that, you will see that you have a null matrix. So this is how you can prove the Cayley-Hamilton theorem for a 2 cross 2 matrix in general. Okay, there exists a general proof for n cross n matrix also. For the timing, do it for 2 cross 2 matrix. So according to Cayley-Hamilton theorem, a matrix satisfies its own characteristic equation. Satisfying means just put lambda equal to A into the characteristic equation. With if you have some constant also put unit matrix with that of that order and simplify. You will get a null matrix. Let us do a problem on it now and see how Kelly-Hamilton theorem can help us in certain problems. First, verify Kelly-Hamilton theorem for A equal to 1, 2, 3, 4. The equation, the characteristic equation for this matrix is, you can find yourself, A minus lambda I2 equal to 0. So if you put this A here and simplify, you will get lambda square minus 5 lambda minus 2. Can you confirm it to me in the chat box? Is it correct? Okay. Now verifying Kelly-Hamilton theorem means solve A square minus 5A minus 2I2. Means in the left hand side of the characteristic equation, put lambda equal to A, and in place of this constant, with this constant multiply I2 and simplify it. Okay, I'm writing the final step. Multiplication you will do yourself of the matrices A with A. You will get 7, 10, 15, 22 minus 5A means 5, 10, 15, 20 minus 2I2 means 2, 0, 0, 2. You can see it is null matrix. Do the calculations, you get null matrix. Is it correct? Okay, good. Now, from this equation, A square minus 5A minus 2I2 equal to null matrix, can you get A inverse? You know, there is a procedure for finding A inverse, general procedure. What is that? You find adjoint A, then divide it by determinant A. I don't want to use it. I want to use this output of Kelly-Hamilton theorem to find A inverse. How can we do this? Pre-multiply or simply multiply by A inverse on both sides. See what do you get. Both sides of this equation. A square pre-multiplied by A inverse means you are left with A only. 5 times A inverse times A means I2. Because if A is multiplied with its inverse, you should get anti-matrix. Minus 2 times A inverse I2 means A inverse only. Is it correct? The expression that I've written is correct or not? Okay, from this, what is A inverse? It is 1 by 2 times A minus 5I2. Correct? I have separated A inverse. Now you know what is A, you know I2, just you have to simplify. And you can write A inverse comfortably. Tell me what is your answer. Is it minus 2, 1, 3 over 2, minus 1 over 2. Is it the final answer for a inverse? Okay. So Kelly-Hamilton theorem can provide you inverse of a matrix without solving adjoint, etc. Means it is a powerful result. For finding a inverse, just you are solving the powers of a, or even in this case, you are not solving even power of a. A very simple result you are getting. Now see another example. This will also make you understand why Kelly-Hamilton theorem is so powerful. This is an interesting example you will not find in the books usually. Find a power 78 where a is equal to 2 minus 1, 2, 5. Use Kelly-Hamilton theorem to do it. Indeed, you will do that. But if you want to do it directly, you have to multiply a 78 times. Will you do that? You will never do that. So we have to do some smart work here. Let us use Kelly-Hamilton theorem to find a power 78 from this given a. So first find the characteristic polynomial, or you can say characteristic equation. If you don't put equal to 0, it is characteristic polynomial. So first find the characteristic polynomial of a. This, or you can find this also, no problem. Both way it's fine. Can you solve determinant lambda I2 minus a or this given a? It should be lambda square minus 7 lambda plus 12. Is it? You have found characteristic polynomial. So what is characteristic equation and eigenvalues of a? What are eigenvalues of a? 3 and 4. Eigenvalues of a are 3 and 4. Okay. Now tell me, if I divide lambda power 78 by this expression, by the characteristic polynomial, what do I get? Lambda square minus 7 lambda plus 12 into some function of lambda, that is your quotient. This is divisor, this is divisor, this is quotient. I don't need to write quotient. Plus remainder, I am sure what I will get. A linear expression in lambda. Because you are dividing by a quadratic polynomial, so remainder would be a linear polynomial. Am I right? When you divide P by Q in numbers, you know, what do you get? Q1 plus R. Do it or not? Q1 is the quotient. Q is the divisor here. Or let me write something else. R some other thing. Numerator over denominator. If you divide n by d, what do you get? D equal to n times q plus r, where q is the quotient, r is the remainder. Don't you know this? If you divide 22 by 3, can you write 22 like this? 3 into 7 plus 1. Is it clear? This is q, this is r. 3 is the divisor. Same thing you are doing with lambda power 78. You are dividing it by quadratic polynomial. So till power 2, you will be dividing. You will leave the division when linear expression in polynomial, linear polynomial in lambda is left. Correct? So this is division algorithm. I think you are familiar with it. All right. Now, this is correct by division algorithm. Put lambda equal to 3 and lambda equal to 4. First put lambda equal to 3. What do you get on the left hand side? 3 power 78. Here if you put lambda equal to 3, because lambda equal to 3 makes it 0, this expression. So you are left with 3a plus b on the right side. When you put lambda equal to 4, similarly you get 4 power 78 equal to 4 times a plus b. Correct? From these, can you find a and b? From these, a is 4 power 78 minus 3 power 78. B is 4 times 3 power 78 minus 3 times 4 power 78. You can check. These are simple calculations. Two linear equations in A and B. I have just found A and B. Right? Now, in this expression again, lambda power 78, this whole expression, put lambda equal to A. See what do you get? You get A power 78 equal to a square minus 7a plus 12I2. That is null matrix by Cayley-Hamilton theorem. Am I right? Am I right? This is null matrix because a square minus 7a plus 12I2 should be 0 by Cayley-Hamilton theorem. 0 means null matrix. So you are left with a power 78 equal to a times a you have already found. A times a means a is given to you 2 minus 1, 2, 5. 2 minus 1, 2, 5. And b times I2 means 1, 0, 0, 1. A and b you have found. If you want to put here, you can put. Otherwise, you can simply combine these two matrices and write your answer. You can write your answer 2a minus a, 2a, 5a minus b. This is the result of a power 78 where a and b are given by these values. Got it? So it is a very good problem. You see how we have solved it. I tell you again, A is given to you. You were asked to find A power 78. First, you found the eigenvalues and the characteristic polynomial. So what we did after that, we found that lambda equal to 3 and 4 are the eigenvalues. Then I divided lambda power 17 by lambda square minus 7 lambda plus 12 with a purpose. You can see later. So by division algorithm, there is some quotient plus remainder. Remainder is linear polynomial in lambda. That I have explained already in detail. In this expression, I have put three things. Lambda equal to 3, lambda equal to 4, and then lambda equal to a. 3 and 4, when I put, I get two linear equations in A and B. And I'm able to solve A and B. By putting lambda equal to a, I'm able to get a power 78. And I'm using Cayley-Hamilton theorem in between. After that, it's merely a calculation. So you see, Cayley-Hamilton theorem can provide you inverse of a matrix. It can provide you arbitrary, means any large power of A very easily. So it's a powerful result, the Cayley-Hamilton theorem. So with this, the first unit, that is of matrices, is over from my side. You can practice more problems on this. So overall in this unit, what we have done, let's recall one by one very quickly. In this unit, first we have learned how to find eigenvalues and eigenvectors of a matrix. By up to this lecture, you are able to understand the importance of eigenvalues and eigenvectors. You can also read practical applications of eigenvalues and eigenvectors on the final page of the lecture notes. So in this unit, basically you have learned the machinery, the mathematical machinery of finding eigenvalues and eigenvectors of a matrix and their properties. Not only that, you have also learned when we say two matrices are similar. If a matrix is similar to a diagonal matrix, then it is diagonalizable. So you have learned how diagonalization diagonalization of a matrix is connected with its eigenvalues and eigenvectors. Correct? So first eigenvalues and eigenvectors, then properties of eigenvalues, then similar matrices, diagonalization of a matrix. You see the connection, how diagonalization of a matrix is connected with the eigenvalues and eigenvectors of a matrix. Then you learn that similarity of matrices is very useful in finding higher powers of a matrix. Then you learned about diagonalization of a real symmetric matrix. There are some very useful results. Norm of a vector, orthogonal vectors, their dot product, orthonormal matrices. Then how can you convert a linearly independent set of vectors to an orthogonal set of vectors by Gram-Summit process? Then a very important result about a real symmetric matrix. If A is a real symmetric matrix of order n cross n, then A has n real eigenvalues, A has n linearly independent eigenvectors, A is diagonalizable, eigenvectors of A corresponding to different eigenvalues are mutually orthogonal, and there exists an orthonormal matrix P with columns as linearly independent eigenvectors of A. that diagonalizes the real symmetric matrix A. Okay, then you learned that how that orthonormal matrix related to a symmetric matrix is connected with the quadratic form, the diagonalization of quadratic form. And today we have done Cayley-Hamilton theorem. So all results are interrelated and very useful applications. So hope you have enjoyed all these lectures and you will be comfortable in doing problems from the textbook. So next time we will begin the discussion of next unit, multivariable calculus. I suggest all of you to watch first two lectures which are already recorded and available alongside the lecture notes. First two lectures you should watch very carefully and try to understand what is explained there. So in the next class, I will take up your doubts from multivariable calculus. Okay, thank you. We will meet in the next class.